AI is. You guys heard about Microsoft is already incorporating ChatGPT in their Teams Meet application. All right, you might want to read about that one because I think even though it is not relevant in this class, I think in the longer run, it is relevant to your future. So I think ChatGPT is not necessarily a bad thing, but you have to understand how it is going to affect you, when it is time for you to go out there, look for jobs. So any feedback from you guys as I continue to try to set up this whole thing? It takes me a while to do this. No questions. You can always take the approach of well, when it does happen, I'll handle it. But only then will I handle it. All right, so we got that. And let me see, I got a earlier thing. Let me see, because I think someone is going to sign in. So it's already recording, so that's good. And I need to look at the participants. There we go. Oh, okay, I need to admit. There we go. All right. All right, so we are recording, and I'm going to start today's lecture with a little exercise. So we'll go ahead and take a look at Joplin, because I wrote the, where did it go? It did not go where I thought it would. Okay, one more time. Maximize over here. There we go. Okay. All right. So the first thing we're going to do is, okay. First thing first. I don't know about you, but I have, I probably have problems, keeping track of what I need to do. So one of the things that can help you is a mobile device. Okay, your mobile devices are getting less and less expensive. So you can use your calendar to track things that you need to do. I can show you, I know it's really small, you cannot really see the details, but I have Google Calendar, showing me everything that I need to do on my home screen on my phone. So the first thing I see when I unlock my phone is what I'm supposed to do on that day. The appointments, what I need to do, the meetings, and so on. And it also includes reminders, okay, things that I need to do by a certain time. So this way I know I got a class right now. And then in some other class, I have, the students have a reading assignment due. So I think that's really useful. And if I go back to the browser, in the announcements, I sent out a link of one of the things that I wrote, few semesters back. So, this is a link to a Google Doc. And in the Google Doc, there are also other links to help you understand how to incorporate all the dates on Canvas onto your mobile device. So as long as you add your WID at apps.losreals.edu as one of the accounts on your mobile device, then the Canvas dates will show up. So when your homework assignments are due, when anything that shows up on the Canvas calendar will also now show up on your mobile device, which I think is helpful to some students, and so for some other students, it may not be as helpful. So, just a resource for those of you who think, hey, I can use another thing to help remind me, what I need to do, what is due at what time, and so on. Personally, I think it's great. If I were a student, this would have helped me, if I was a student today. Yep.
Speaking of dates, what is the first test?
What is the first
test?
It's going to be in about week 5 to 6. This is the beginning of week 4. So I think what I'll do is next week, I will give you guys what I would call I used to call it a practice exam, but I don't want to call that, a practice exam anymore. I would just call that an exam from the previous semester. All right, so we'll go over that, okay? I can give you a test to begin with. It's not count to your grade at all. It is just for a way for you to practice and also to understand the scope of your own exam. And then I'll go over it and give you the correct answers to all the questions. So I think that's one way to get prepared for the exam here. But you always have 1 week between the time that I go over the practice and the time that you actually take the test. So there's always that week in between that you can ask additional questions, also to ask questions about what you can do and what you cannot do during the exam. So that's a very good question to ask. Let's see, let me check my Joplin, because that's also how I track what I need to do. Assignment. Okay, so we do have an assignment now. It is assigned today. It is due in a week. Okay, so if I go to functions, so just functions is the one that I just assigned this morning. If you have not checked that, this is active now. Once again, it is important to understand you only have one attempt. So if you're used to the way that I do my CISP440 lab, this is not one of those. Okay, you cannot do an infinite attempt approach. So you can only submit once. Once you submit like the previous one, that's it. Okay, but you do have until next Monday at noon to turn it in. So you can always start. Okay, you can start even now. Okay. And then just continue to work on it. If you encounter a question and you're not quite sure about the answer, you can ponder, okay? You can think about it. You can just kind of spend days to think about it. You just have to make sure that you submit your answer by the time when the assignment is due, which is about 1 week from now. Is that okay? So here's another question. What if I make the due dates, kind of flexible? Is that a good thing or is it not a good thing? Considering that usually I give you a week, for the homework assignments instead of I want this to be done by Wednesday. That might be a little tight, but a week. What do you think? No comments.
And that's like if you go over it. It's helpful if you go over it in class. So if you don't do that, then you do later. That's hard to know.
I can respond to questions. In other words, if people have started on this one and have encountered some challenges, like I'm not really sure what you're asking here, or I don't know what this symbol is representing, then we can talk about it in class. But it is difficult for me to actively talk about it because I am not a mind reader. I cannot see what questions you have in your mind. And as such, I cannot preemptively answer questions. Does that make sense? So if you guys start on it and you have a question, I can respond to those questions. But on the other hand, if I don't know what you do not know, then I do not know how to respond to those questions. So that means if you start early, if you start on these, before Wednesday and you give it a try and then you go like, okay, I absolutely am stumped. I do not know how to proceed from here. Then we can talk about it on Wednesday. I can respond to those questions. Otherwise, I don't know what to do. I don't know what to say about it. Is that all right? Okay, so getting started early is important. Interestingly, there are some people who say, well, we should allow flexibility in terms of due dates and deadlines. So my answer is, once you start to work in the workplace, what if your employer says, we can't really cut your paycheck in time? Would it be okay to be a week late? Well, okay, so you can kind of see how it goes both ways, right? So that's all I want to say. All right, so let me check my Joplin again, just to see. Okay, there we go. So I do have some practice questions just for today. So the first one is, what is the value of blah, 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 blah? Okay. And there are two of those. I want you guys to kind of spend some time to take a look at these and try to figure out the answer to both of these practice questions. Obviously, there's nothing to turn in. And So I don't know how you guys want to proceed with this. There are two ways to proceed. One is I give you guys actually maybe 5 to 10 minutes so they can work on this and then I'll go over it. Two is I'll just go ahead and explain how I would approach this. So which one do you want? Do you want like 10 minutes to work on this first, or do you want me to talk about it?
I would like 10 minutes.
You would like 10 minutes? Okay. All right, so we'll go ahead and time 10 minutes. Yep.
They both do the same thing, right?
They do not. And about 5 more minutes, and you're free to talk to your neighbors. I mean, this is not, there's nothing to turn in. So if you want to talk to the student next to you, that's perfectly okay.
I don't know, the second one says amendment versus. Second one's confusing.
It's the.
Well, I mean, it boils down to that. No, it boils down to.
Oh. Yep.
that's a
Here. All right, good job.
I think
That's
so.
the first thing.
So.
All right, so that's that.
No, every. For all, yeah. Okay.
All right, so there's one missing parenthesis here, and it's going to be the same place over here. There we go. Oops.
The other one, I don't know. It's asking.
He's asking for the X, Y values as well.
No. It's gonna be a Boolean as well, probably, right? Because it's like a bunch of conditional statements and stuff, or logical statements. I don't think it's gonna be X one. You see how we got this one?
Yeah.
Do you agree?
I think so. Could be wrong, but I think so.
Because it's like saying X, Y.
I'm thinking about the same.
I'm just here, just so that everything, is on the same line, makes it easier to read.
I know what it means.
There you go.
Why is so that was. Why contains. Yeah, that's it. And that's all, that's greater than one. So that'd be the first one.
X is an element of three.
And Y is an element by two.
Oh, second. Oh, second one's true.
Yeah. Yeah, that's what I meant, so why?
So X, Y is being defined. So you see, like the very first thing that's, but it's saying the set that's defined by X, Y is defined by that.
I'll stop messing around.
So after that first one, you have X is an element of 1, 3, and Y equals 2, and Y equals those. So all of those define what X, Y. And all of these three agree with each other. X is an element of 1, 3, does agree with the rest of them. That's true, that's true, that's true, everything's true. And it's gonna be greater than 1. So I think that's how we do.
So if you want to, yes, I like on each person, Y for the second. Say that.
The only values you can plug in for X are
Is
1.
103 and Y is.
One of those, and
Yes.
I'll get 1, you're gonna get Y is equal to 2, and that's fine, and that also agrees with the Y equals negative. If you plug in 3, you're gonna get 1, 6, and that agrees with the other two conditions, X, and Y equals 2X, and the 3 numbers does not care about. Yeah, because that's just saying in general, Y has to be one of those, not always.
And it's just X, Y, and 3 doesn't want to.
Yeah. Yeah.
Specifically X, Y.
Wait,
And then two bull.
so that's actually a good point. Oh, no, it's looking at the cardinality. It's looking at whether there's more than one thing is the setting. It's the whole thing is. There we go. That's good.
So we that's testing.
The bars are cardinality. Dude, that is so confusing. The double bars are cardinality, but there's a bar inside.
The first one.
No, the first one, the cardinality is 0. Therefore, that's pretty sure, right?
It's not looking for less than one, for only 2 possible values. Here's 63 and 6341. And then what the set is 63 and two values in that set, which means the cardinality is 2.
Wow.
2 is greater than for the second one, I mean, so at least assuming that's the
But
cardinality.
no, but the cardinality one is right, but the whole thing is false, I think, because it's saying all x is an element of 1 and 3.
All X's
All
are.
right, well, 10 minutes is up. As much as I would like to give you guys more time, I think it's kind of important to keep the class going. So I'm glad that you guys are having conversations, okay? Talking to your peers can be very helpful in terms of, gaining a better understanding of the material, because the pathway in your mind when you're listening and the pathway when you're trying to form sentences to explain it to somebody else, those are two different pathways in your mind. So it's good to exercise both of them in addition to the visual, which is, you try to process this using your eyes. So it's the third way. All right, so to answer the questions, both of these are Boolean, okay? They're either yes or no. And the reason why is because eventually for the second one especially, we are only looking at the greater than right here. So whether something is greater than 1 or not is either true or false. For the first one, even though there's a quantifier outside, the quantifier is really just saying, we need this whole thing, which is also a comparison to 1. We need this to be true when x equals to 1, but we also need it to be true when x equals to 3. That's what the universal quantifier is trying to say, is whatever is inside the parentheses, starting from here and ending all the way over here, that thing has to be true when x is 1, and it also has to be true when x is 3. Is that okay? So the answer to both questions should be Boolean, okay? It's true or false. Okay, so we'll go ahead and look at the first one first and try to figure out what the answer is. So for the first one, the first thing I'm going to do is to say, well, this is not too bad, because I can just say, what if x just equals to 1? Okay, so we have what if x equals to 1 and blah, blah, blah. Okay, so this time I am putting an extra constraint and say, well, let's not consider the entire set. I am just looking at the very special case when x equals to 1. Is that okay? Because that x is in the set, okay, which is part of the filter of what do we care about? Okay, x is a universally quantified thing, but it has to come from the set, which only has 1 and 3 in it. So now we have to evaluate the thing inside the parentheses, starting from, okay, I have a bad habit because I forgot that there are people online. There's one person online. So we have to evaluate this whole thing here. But since we know x equals to 1, so that means wherever you see x, we can just kind of say that's 1, okay? So I can say this is a c dot 1, c times 2 times 1, and that's it, okay? So now it makes it a little bit easier to evaluate, because now we can see on this side, all the occurrences of x are now replaced with the actual value of 1. So now the question is, we see the set notation thing, what are we really asking? So the first thing you need to do is to look at, what are we comparing to 1? We are looking at the cardinality of a set to 1. We want to see if it's greater than 1. What set are we talking about? What is in this particular set? So the way we have formulated, this set is that every element has the format of a 2 tuple. The first item has to be a 1. The second item, is y. Okay. So that's the format. That's the constraint of what each element should look like. Okay. So what can be y? Well, this bar here is not a part of the cardinality. This is a part of saying such that. Okay. So whatever is on the right-hand side of this bar is a constraint of, this has to be true. Everything from this open paren and everything all the way up to this closed paren here, it has to be true for every y that we are considering. Okay, fine. What constraint are we talking about? Y has to be 2 times 1. That's easy. That's 3, right? Okay. And this is conjunction. So by now, we should know that means conjunction, okay? Because if not, I think we are in some trouble. Yes?
Did you say 2 times 1 is 3?
Hmm?
Did you say 2 times 1 is 3?
Yes, and I was wrong. 2 times 1 is 1, sorry. So 2 times 1 equals to 2. Okay, very good. So 2 times 1 times 2 is 2. Okay, all right, fine. That's a very good excuse, yes. So y is 2, okay, so this means that y is 2. And y has to be an element of 2, 4, and 6. That's a set. So we need both of these to be true. Well, can we find a y to make both of those true? Y is 2, right? Because y is 2 makes y equals to 2 true. And it also makes 2 as an element of the set 2, 4, 6 also true. So we can find at least one element in this particular set now. The question is, can I find another one? The answer is we cannot. Because y is constrained to be 2 because of this equality. So that means, this entire set, the set that I'm constructing, basically from here, all the way up to here, only has one single element when x equals to 1. So that means this whole thing is false. So I can say now is, okay, equals to false, which in my class is represented by a 0. So you can pretty much conclude right away and say the quantified statement itself is also true. Because if you look at the quantified statement, which is the one right above it, it needs, when x equals 1, we need true. But when x equals 3, we also need it to be true. If one of them is false already, I'm done. I don't even need to evaluate the second one because the first one is false already. So that means I can now go back and say, this one is false. The entire thing is false. So if you want me to give you an extra pair of parentheses, we can start all the way here and then go all the way here. So this 0 here, this 0 means false. It does not mean numerical 0. Yep. Why is it false? Okay, which one? Are we looking at the quantified one or the non-quantified one? The non-quantified one? Because the non-quantified one is assuming that x equals to 1. All right? Because x can be 1, x can be 3. I'm just choosing 1 to be the first one to evaluate. Is that okay? Yes. So when x equals to 1, instead of looking at x and x over here, I just say, x is 1, so might as well just use the constant of 1 over here. All right? So we can find exactly one value for y to satisfy this particular conjunction. Is that okay? Yes. So that means this set here, from here to here, has one single element, which is the 2 tuple of 1, 2. Is that okay? What is the cardinality of that particular set? 1. Is 1 greater than 1? There you go. Is that okay? Yep.
So how do we make that statement not a Boolean and make it like creating a set?
Creating a
Like instead of saying it's true or false, we just like, I don't know how to say it, but just like to make a set, like the answer is like another set.
Okay, I think the second example is easier for that setup, so I can answer the question in the second question. The first one is much harder because of the universal quantifier. Whenever you work with a quantifier, the parenthesized expression after the quantifier always has to be Boolean, and then the quantified statement also has to be Boolean as well, because you're asking a question. Is it true or is it false that every blah, 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 blah? Okay, so it's either true or false. Does that make sense? Okay, so let's take a look at the second example. So the second example, it's actually easier to look at it the way that you suggested. So what I'll do is I'm going to make a slightly different question first. So I'm going to ask you, what is the set W if W is defined exactly like this? Okay, So it's a slightly different question, but nonetheless related to the actual original question. So we'll try to answer the question of what is W. So in this case, W is a set. How do we know? Because the way we define W, uppercase W, is open brace, close brace, and with some stuff inside. That is the notation of, oh, we're dealing with a set. The second question is, what is in this particular set? What are the members of this set? So to answer the question of what are the members of this particular set, we look at the bar notation here. The bar notation is basically saying, what does each element look like, okay? And such that, what are the constraints that is applicable to the elements? Is that okay? In other words, okay, I keep pointing to the screen instead of using a mouse pointer here. So with this one, we are looking at, this is the format of what each element looks like. And then this part here specifies a constraint of, that needs to be true for every element in this set. Or if it is true, then that thing belongs to this particular set. Is that okay? So now the left-hand side of the bar tells me that every element has to be a two-tuple because that is the format of a two-tuple. Okay, the first thing in the two-tuple is called X. The second thing in the two-tuple is called Y. So at this point, I do not know what the constraints would be. But then when I read the right-hand side of the bar, which is the such that blah, 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 then we have the constraints. So the constraint said X has to be an element of 1, 3, and Y has to be 2 times X, and Y has to be an element of 2, 4, and 6. Those are constraints. I need all three to be true. Why? Because the three expressions are joined by conjunctions. Okay, we have a conjunction here, we have a conjunction here. All right, so now the question is, how do we process this? Well, fortunately, this is a finite set, so is this as a finite set. So that means we can just evaluate, okay? We can just go ahead and evaluate and find out all the cases. So I can now say, what if X equals to 1? Okay, if X equals to 1, it certainly meets the requirement of X is an element of 1, 3, right? So if X equals to 1, this is going to be true. And then the second one is now constraining Y to be exactly 2 times 1, which is 2. Yes, I learned from a mistake. 2 times 1 is not 3. And then the last one says, now that we know Y has to be 2, is 2 an element of 2, 4, and 6? The answer is yes. Okay, so that means one element that can exist in this particular set is having X being 1 and Y being 2. That's one element. Can we find other elements in this particular set? The answer is yes. You guys are nodding already, because when X equals to 3, then Y equals to 2 times 3, which is 6. And 6 as an element of the set of 2, 4, 6 is also true. So that means there's another element in this particular set being 3, 6 as a two-tuple. So that means when you look at W as a set, it has exactly 2 elements, 1, 2, and 3, 6. Yes. One tuple is not particularly useful. So a tuple is an array, a two-tuple is an array with 2 items. All right, so those terminology is important. This is something that we talked about in week 1, and we are at the beginning of week 4. So it's really important to get those terminologies down now. Okay. All right, so that means W has 2 elements. So now we can answer the original question, which is looking at the cardinality of W, because W is the whole big mess inside the braces. And then we ask here, what is the cardinality of W? It is 2. Is 2 greater than 1? The answer is yes. Yep, go ahead. The 4 in here?
Yeah. Does that have to go after the 4 as well?
Well, I mean, this, okay, so let me want you to use the mouse. I can actually do this. It's gonna go. Yes. So this part here is merely a constraint. All it says is this element of has to be true in order for a particular two tuple to be an element of the set. Well, okay, so let's say, you choose, y to be 4, okay? So if y is 4, then y is an element of 2, 4, 6 is going to be true. And then going backwards, if y is 4, then x has to be 2, right? And then we go back here. If x is 2, 2 is an element of 1 and 3 is false. And what happens when you have one false in a long conjunction? The whole thing is false. So that means if x being 2 and y being 4 does not meet this entire constraint here. And as a result, 2, 4 cannot be an element of W. I need to make myself a little strap thing so I don't have to hold on to it. So I can just do this. Yep.
So the distinction between the first one and the second one. The first one only looking at elements 1, 3 for X. And then it's testing the entire equation using that specific value.
It's looking at the conjunction. Technically, it is looking at the conjunction of x equals 1 and blah, 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 and x equals 3 and blah, 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 blah. So it's looking at the conjunction of the two because it wants this part here. It wants this part here, this entire thing, to be true when x equals to 1, but it also needs to be true when x equals to 3.
So for that one, so you have to test both x's x values individually to see if they both work. For the second one, we're trying to find the possible values for W. And if those cardinality of those values are greater than 1, then it's true.
If the cardinality of W is greater than 1, then the original question would have an answer of true. Yes. Is that okay?
So what tells me that? Is it the quantifier is fine?
Yeah, I mean, the quantifier, basically completely signifies that the answer should be true or false. Okay, let me go back to the professor question. Every professor at ARC sucks.
No.
Okay, so no, but what is the type of answer to that question? So is the answer a list of professors at ARC who sucks, or is it a yes/no answer? Let me repeat the question. Every professor at ARC sucks.
Say yes, no. Say yes, no.
It's a yes/no. Exactly. It's the same thing here, except this is how we say every professor at ARC. And this part here is the professor sucks. And we are asking, well, yeah, that concludes the entire. So you have to be able to relate the analogy to the expression itself. Because every time you ask every, the answer is automatically yes, which is Boolean. Now, the second one was, the original question is still Boolean because I'm asking is blah, blah, blah greater than 1? Okay, so what kind of answer do you expect? Do you expect a numerical answer or do you expect a yes/no answer? A yes/no answer. So it's a Boolean. But when you only focus on this part here, starting with looking at the W, it is a set. So that is now the result of that is going to be a set. What things will meet this requirement? Give me a list. Okay, obviously it's not a list because it's a set, and in a set the ordering does not matter. Right? List it does. Is that okay? Are there any questions about these notations? Yes, go ahead. The cardinality of the set has to be greater than one, yes. Yep. Yep.
The cardinality of the set is just how many.
The
Sorry,
num-
not of the set, of the. Oh. there's two different things.
Yep. The cardinality refers to the number of elements in the set. So it's just a fancy word of number of elements. All right. So this is a, once again, there's nothing turned in. I'm not recording your answers. I'm not grading or giving you guys a score, but this gives you an idea of, whether you're understanding the notations and understanding, how to read a notation, how to read a combination of the notations that we haven't talked about before. Is that okay? All right. So once again, if you have any questions, my office hour is right before this class. So, that would be a great time to come talk to me, and also, about half an hour after this class, I typically have time as well. So if you want to just kind of follow up on a particular thing that we talked about today, that would also be a good use of time. All right, so now we are I'm going to take roll because, I think you guys can take a short break from the content of this class. So we're gonna take row. Oh, and the row taking thing is this one here. Today is the 6th of February, and we are in the 4th week of the semester. So we are almost 1/4 done with this entire semester. And the access code is Wheatstone. So let me write it down, all lowercase, Wheatstone. Okay. Yes, it is. And the reason why I chose this particular term has to do with today is the birth date of Wheatstone, who invented a particular type of circuit that is used today, a lot in any types of sensors. So I'm going to say I am in class today. I forgot to change the type of question, so we'll turn it into true, false, update question, save and publish. So now if you refresh your browser, you should be able to find the row taking activity for today, which is 2023-02-06. And the passcode is Wheatstone. Look it up, Wheatstone circuit. It's actually called Wheatstone bridge, which is a really interesting way to acquire high resolution reading from an analog sensor. Yep.
Not seeing that, let's see here.
You guys are not seeing it? It says it's refresh. I can try to make a QR code out of it. Let me see if I can do that. Okay.
So do the function.
You can put a due date.
Yeah, okay.
You can put a due date.
I did not put the due date. Oh. Right, I forgot. All right, fine, I'll put the due date now. Without a due date does not mean that you cannot participate. It simply means that it's indefinite in that case. So I'll put it a due date at 1 o'clock. That's plenty of time, I hope. And I'll do this in super slow motion. All right. So are we good with the road taking activity? Is anyone still working on that one? Okay.
Now I have a question. Where in Canvas do you put the lecture videos? Or do you post all of them or just some?
They're on YouTube now. I think, but I'm not sure. The recordings. This is on here. There you go. Yeah, so I already announced that the recordings will now be on YouTube. And the YouTube channel is some props. So if you just go to youtube.com, just type some props, that's the channel. Right. All right, so we are now continuing with functions, and this time we are going to continue with injection, surjection, and bijection. We started on this already last Wednesday, which is 4 days ago. So I hope you guys have a good recollection of what we talked about last Wednesday. So injection means, everything in the domain needs to map to one and only one unique things in the codomain. That's essentially what it means. And then the notation I choose to use is this here. Okay, so if you already know that f is a function, this is going to tell you whether it is also injective or not. Okay, so when I say this, I am referring to for all q in y, which is our codomain, pq such that pq is an element of f has to be less than or equal to 1, which translates to, if you look at each element in the codomain, you say, hey, element blah or element q of the codomain, are you mapped from at the most one thing from the domain? That's basically what it's asking. And every element in the codomain should be mapped from up to one thing in the domain. Because the moment you have two things mapped to that one thing in the codomain, then you have a non-unique mapping. Because now you have two things in the domain mapped to exactly the same thing in the codomain, it's no longer unique. So that's what we talked about last Wednesday. What we'll talk about today is surjection. So surjection is over here. A surjective function, aka also known as a surjection, is a function where every element in the codomain is mapped to. So that means we are utilizing everything in the codomain. There's nothing in the codomain that remains unmapped to. Is that okay? Just the English interpretation of what is surjection. Is that okay? Are there any questions about that particular statement? So one way to do it, one way to qualify whether a function f is surjective or not, is to express it this way. Now, so what does it say here is for every, yeah, go ahead.
My question was, do they have to be mapped to a unique?
Nope.
Okay.
So you can have injection, but not surjection. You can have, you can not have injection, but you can have surjection. You can have both. You can have neither. Okay, so later on we can show examples. So in this case, one way to express whether f is surjective or not is to ask this question. So once again, what is the answer to this question here, where the mouse cursor is? What is the type of answer to that question? Does it return a numerical value? Does it return a set? Or does it indicate something that's either true or false? True or false, okay? Because it is a quantified statement. So now it is asking for every q in y that should exist a p in x such that f of p equals to q. So that's one way to look at it, okay? The second way to look at it from the set notation is this thing here. So this thing is now saying for every q in the codomain, if I look at the cardinality of this thing here, it should be greater than or equal to 1. What set are we talking about? The cardinality of what? The cardinality of a set where PQ is an element such that PQ is an element of F. Now P is free floating. In other words, P can be anything such that PQ is an element of F, but Q is already bound to a specific element because of the quantifier. So it really is saying the same thing as the first one. It's just expressed in a different way. Are we doing okay so far with both of these definitions? As an example, okay, so I'm just going to go with the example here. So I'll skip this one and go for this one here. So we have f being a function, is known to be a function. The domain is AB, the codomain is 1, 2. So now we have f defined to be A1, B2. That is surjective because from the perspective of the codomain, which is the 1 and the 2, you now ask, are they both mapped to? I think so, because one is mapped to from A, and then two is mapped to from B, and that's it. There's nothing else remaining in the codomain, so everything in the codomain are mapped to. Is that okay? Does everybody understand why the first example is indeed surjective? Okay, the second one is not. So when you look at the second one, it is not surjective. It is still a function, but it's not surjective. Because when you look at the two elements in the codomain 1 and 2, you can say, one is okay, it got mapped to. Now, is it once, is it twice, is it like multiple times? I don't care, as long as it is greater than or equal to 1, we're good. But when you look at 2 as an element of the codomain, nobody maps to it. It's not used in the function. So now the second example is not surjective. It's still a function, it's just not surjective. Are we good so far? So now we go back to the earlier example of what if I have a function where the domain is AB and then the codomain is 1, 2, 3, then it can never be surjective. Because as a function, we know that only 2 out of the 3 elements in the codomain can be mapped to. Because there are only 2 elements in the domain. So no matter what you do, there's always at least one member in the codomain that is not mapped. And as a result, that cannot be this particular function here. Oops, I need to get back to the slide. This function, no matter how you define the actual set of f, it can never be surjective. Can it be injective? Sure, can definitely be injective. Can it not be injective? It cannot be injective, but it simply cannot be surjective. It has to be not surjective. Yes?
Does that mean that the domain and the codomain have to be the same size?
Okay, it depends on what you want. If you want the function to be surjective, then you only need the domain to have a cardinality to be greater than or equal to the cardinality of the codomain. Okay. So we doing okay so far with the concept of surjection. Okay. So bijection is super easy once we understand injection and surjection, because it means it's both. So a bijective function, also known as a bijective function, also known as a bijection, is a function that is both injective and surjective. This is actually where we want to get to, okay? Because in something that's injective but not surjective, not particularly interesting. Something that is not injective but surjective, not very interesting. But things that are bijective, now we are talking about something that can be useful in many situations. So when we look at the definition of injection, this is the definition of surjection. Do you see a similarity between those two definitions? Okay, let me go use a mouse pointer. When you look at this particular statement and you look at this particular statement, do you see they are related?
They can both be one.
Hmm?
Cardinality from both can be one. So if they can equal to 1.
They both relate to 1. One needs to be less than or equal to, the other one needs to be greater than or equal to. And once I say bijection is injection and surjection, that means, oh, okay, so they just have to be equaling to 1. Okay, so now we have the number of, okay, so let me go back to the definition of injection and surjection. So bijection means everything in the domain maps to one and only one unique element in the codomain, and every codomain element is used. That's basically what it's saying. So now the question is, so what? Well, when you have a bijective function, it's reversible. You can go one way and then you can go back. So if you are given the value of f of x, you can go back to figure out what x results in f of x, the value. So I can give you a very simple example. Okay, I'm just doing this on the whiteboard because it's really a simple example. So if you think about a plot of y equals to x in in your algebra class, okay? If I give you the y, of a particular pixel on this line, do you think you can find the x? You guys go like, yeah, but that's because they're exactly the same. Fine. What about this one? What if y equals to x divided by 2? If I give you the y, can you figure out the x coordinate of that pixel? The answer is, yeah, we can solve that. It's basically just that, okay? If you give me the result of applying the function, I can figure out what was mapped to that result of the function, and vice versa. Is that okay so far? All right. So that's why in section 5 here, we talk about inverses. So a bijection is reversible. In other words, given a bijection, f, using x as a domain, y as a codomain, there's a bijective function or bijection, f inversed, which reverses the roles of the two sets. So in f inversed, what used to be the codomain now becomes the domain, and what used to be the domain now becomes the codomain. And we have a further qualification of the reversed. So for every element in X, F inversed applied to F of E has to equal to E. And vice versa, for every element in Y, which is our codomain, F of F inverse of E has to be E. Are we good so far with the concept of inverses? All right. So we're going to move on. So the proof is, this part here. This is the proof of why a bijection guarantees to be reversible, and there has to be an inverse function. All right. So that's the entire proof. If you're not interested in the proof in this case, you can kind of skip this part. But on the other hand, if you want to make sure that you really understand the notation that we have used up to this point, reading through that proof is a good exercise. Is that okay? So this is all I'm gonna do. Okay, I'm not the kind of guy who would give you like tons of homework assignments and force everybody to do the homework assignments. I'm kind of the doctor who would tell a person with diabetes is like, eating all that candy may not be good for you. But ultimately, it's up to the patient to decide, do I want to kind of not eat that candy, or do I want to kind of give in to the temptation, and just eat all the candy? Well, it's up to the patient. The doctor, I just give you the information, my opinion, and what I think will be in the future if you do this. But what people choose to do is up to that person. Is that okay? All right. So I'm just saying that reading through this proof is going to be beneficial if you want to have another exercise of trying to be more familiar with the notations. I think it'll be helpful. So what I do want to talk about is to go back to the sorting example. Okay. So remember, we were having a lot of problem expressing the post condition of a sorting algorithm, that is supposed to be doing in-place sorting in an array. So what does bijection have anything to do with that? Okay, that becomes the question. So I'm going to switch to Joplin because I want to type the entire thing. So I'm going to start with this one here. Okay, so given an array, the array A, and the initial condition is okay, so I'm going to add another set just for convenience. Okay, define uppercase I to be a set where x such that x is an integer. You can make it natural numbers, and x is less than a bar or the length of a. Okay, so let me just kind of, you guys remember, focus on the right hand side. So I'm using a lowercase a to denote an array as the input of the sorting algorithm. And then define I just, as a convenience item. So I is basically just representing the indexes, the valid indexes into the array A. Because bar A bar is giving you the number of elements in the array. And we know that the last element of the entire array has bar A bar -1 as an index. So I, uppercase I, is nothing more than a set of valid indexes into the array. Which is convenient because otherwise I would have to redefine that set all the time, which is not cool. Are we good so far? All right, okay. So now we can say, okay, so we are also given that K of I equals to A of I prior to the execution of the sorting algorithm. So this is basically just a way for me to define the initial values of each element of the array A. It's K of I, okay? Is that okay? So K of 0 is the initial value of A bracket 0. K1 is the initial value of A bracket 1, and so on. Because I need to keep track of what were those values to begin with. We good? Okay. So now we can focus on what we are really trying to get to. So what is supposed to be the post condition of a in place sort on array A? Okay. So we are attempting to answer that question now using the notations that we have already taught. The first one is easy. Okay, everybody knows this about sorting algorithm. A bracket I should be less than or equal to A bracket I plus 1. Okay, so let's get it out of the way. So we'll say condition 1. Okay, I'll just, instead of naming it, I'm going to say one of the necessary conditions is. So this one's easy for all. Okay, for all I in I, my uppercase I this time minus RA bar -1. I'll explain why we need to do the difference here, but I need to put a bar here. The following has to be true. A bracket I has to be less than or equal to A bracket I plus 1. All right, so once again, focus on the right-hand side, instead of the left-hand side. All right, so what are the necessary conditions? All right, so what does it mean when I say a condition is necessary as opposed to sufficient? Exactly. So a necessary condition is by itself not good enough. It has to be true, but even if a necessary condition is true, it doesn't mean the sorting thing is done. Is that okay? So this has to be true, but it's not the only thing that has to be true. So this one, do we intuitively understand this one? Like, yeah, after the algorithm is done, every next neighbor has to have a value that is greater than or equal to an element in the array. That's intuitive, okay? So the reason why I need to do the difference, which is this operator here, is because if I don't do this, then the last I is going to be the index of the last element already, and then I'll be comparing that to past the end of the array. So that's why I have to take that one index out of the set. Otherwise, it will have an array index out of bound type of thing. Is that part okay too? All right, okay. So the second one is going to be the fun one. This is the one where we want it to be why surjection is useful. So the second one is going to read like this, okay? So another necessary condition is, all right, so this one is going to be long, okay? So we'll start with there exists, okay? There exists F, okay? And F has to be a function, okay? So such that F is a function mapping from I to I. Okay, so that's the first thing we need to do is to specify that there exists a function, and it is mapping I to I, uppercase I to uppercase I. So we are looking at a mapping of indexes in the array, into indexes into the array. Okay? But that's not, yeah, because of the I plus one. Because when I is the index of the second to the last element, then I plus one becomes the index to the last element. So that's why we have to take that last one out because of the plus one. Mhm. All right, so such that what? I mean, what do we, trying to specify here? So such that one thing is F is bijective. Aha! So that's why bijection is useful, okay? Because we need this F to be bijective. And all right, so we'll check this out, and then you guys can tell me whether you understand it or not. So we'll say for all lowercase I. Well, maybe I shouldn't use lowercase I. Let me think whether I can use another symbol or not. M and N, yeah, M and N would work. So for all M in I, in parentheses, we say there exists an N also in I, such that A bracket I equals to K, oops, okay. I said I took out I, so A bracket M equals to K bracket. Oh, I don't need that there exist. Let me think, rethink. Right, okay, so I don't need the inner one, sorry. My fault. I mean, I could kludge it so that it's actually used, but I would rather not. So this is going to be F of M. There we go. All right. So this is it. The last one, that for all M in I, A bracket M equals to K of M of M. Okay, so the first thing is, what does that mean? What does that mean? Well, that means for every single index into the array, from 0 all the way up to bar A bar minus 1, for every single one of those, when the sorting algorithm is done, if I look at one particular element in the entire array, it has to equal to the initial value of one of the original items in the array. But then, yeah. Okay, so then the question is, so what if you have 2, 2, 2, 3, 2, 3 in the original array? Is this really going to make sure that the finished array has to be 2, 2, 3, 3, and it will rule out 2, 3, 3, 3, and 2, 2, 2, 3 as possible answers? Will this rule out those things? Why not? So the key is F is bijection. Is a bijection, which means every element post sorting has to map to one and only one unique value from before the array was sorted. So which 2 out of the 2 2s we're talking about is specific. Which 3 is also specific. So the bijection is the key to solve this problem, because it is not just a function, it is a bijective function. Are we doing okay so far with this? Yes, sort of. All right, so let's circle back and talk about why is this applicable? I want to be a computer science person. I want to become a software engineer. I want to become a developer. I want to write code because that looks good. Look at all those movies with all the hackers, really going like that, and then they break into a system. Isn't that cool? It is cool. Except ChatGPT can do that already. So what are you going to do? What is the role of a person as a software engineer? Post chat GPT, yes. Logical reasoning,
Or like having that, like rigorous logic.
okay. So that is correct, okay, in general, that is correct too, yes.
You have to know how to ask the right questions in a way that it can't give the wrong answer.
That is correct as well. Yep. So that is true. So let's think about, okay, let me try to think about an example. Okay. Transportation, okay, cars, okay, how did you get here? Okay, that kind of question. So if you think about a day when Tesla or some other car company finally, finished self-driving cars, okay, reliable, inexpensive, you just flip up your app and go like, I need to go to school, pick me up in 2 minutes, okay? Car gets to your door, get in, and then within the predicted amount of time, you get to the campus, it normally costs you like $2, okay? Or one, okay, it's very inexpensive. So how does that compare to you, taking the bus, getting here, walking all the way, and so on? Well, it's basically, it goes from you doing all the work to just specifying what needs to be done. Does that make sense? Because today you got here because you are the one who had to get out of the house and then walk to the bus stop or drive, okay? Get off at the right place, because if you fall asleep on the bus and you skip this station, you'll be somewhere else. You have to pay attention on the road, okay? And that's how you got here. You are the one who have to kind of like control the entire process. But the objective is really just to get here. How you get here is kind of like, oh, man, do I have to worry about that? Do I have to drive? Do I have to pay attention on the road? That's just like necessary things that you have to do, but not exactly the objective. But in the self-driving car case, you're trying to specify what I want to accomplish. I want to be on campus by this time in order to make it into this class on time. The rest is automatically done. That is the analogy I'm trying to make to tell you, what I think is in the future. So instead of people writing the code, you're going to tell the computer what the code is supposed to do. And then the AI may be able to finish the job for you. Is that okay? So at this point, okay, at this point in time, okay, before, or I should say prior to ChatGPT, how do people write programs? I hate to say it, it's trial and error. They get the instruction of what the program is supposed to do, they write some code, okay, and then they throw it at the wall until it sticks, okay, because there are people who would test the code. It's like, nope, this doesn't work. Why is this not working? This test case does not work. Okay, go back and fix your program. Okay, so it's kind of like an iterative process because the developer, more often than not, did not entirely understand the entire specification of what the program is supposed to do. But it's an iterative process. Okay, I write some code, I finish some code, I give it to the tester, and the tester goes back and is like, nope, it's not working for these cases. You go like, and go back and debug the code and so on. When the AI is capable of writing code, then the question is, can you specify what the program is supposed to do in an accurate way? So I think that is why what we are talking about here is relevant. Because in this particular type of language, and I can tell you many times already, I did embed a lot of things in my classes. This is not one of those. Okay, the math notation has already existed for a long time. And this is how you can describe things in a very precise way. So there are no two ways to interpreting the same thing. So I here for critical coding, this is what is needed. Okay, if you're going to write the code to control a drone that is going to fly over hostile territories, I don't want to get into politics, but that sort of stuff. Okay, you don't want your code to go like, I'm pretty sure this works, on any state in the United States, but if it flies over beyond this territory, maybe it will do the right thing, or maybe it will just do the wrong thing. I'm not sure. That would not be okay. Now, it's okay if you're working for Twitter and Elon Musk, says, we need to find a way to block certain people and then you need to write an algorithm. If you accidentally block some more people or not enough people, it's not the end of the world. Okay, Elon Musk may throw a fit, but that's actually quite enjoyable to watch. So I encourage people to actually do that. Keep poking until it explodes. But if you're on a critical mission, your code is critical, mission critical, you don't have that luxury. And this becomes more important. And I can tell you, the operating system on your phone, on your watch, on your computer, they have a lot of code that is mission critical. Otherwise, people can hack into your phone, they can hack into your watch, they know exactly where you are, which may or may not be useful. Okay, if you're accused of a crime, it may be actually useful. You can establish alibi, but in some other cases, it may not be that good, right? So that is, I want you guys to think about this, okay? Because I don't want you to think about this class as like, it's just another barrier, another obstacle to getting my degree. No, I really want to teach you stuff that is relevant, especially now because of ChatGPT. If it's not for ChatGPT, I can kind of tell you it's like, this stuff, it's good to know, but these days it's like, yes, I think it's going to be relevant. So there you go. I know we are running out of time. I will see you guys on Wednesday. I do have some time right after class if you want to clarify certain concepts, but that part will not be recorded.
Died. I almost imploded because I almost